have Nicholas presenting about a literature survey on planning through LLMs.
Thank you. Okay. Hi everyone, I'm Nicholas Rossetti, and today I will talk about our position paper on current works on planning through LLMs to analyze the state of art, written with my colleague at the University of Brescia. Okay. We have a lot of papers starting from NeurIPS, ACML, ICML, ICLR, ICAPS, ICAPS, AAAI. So a lot of ASTAR conferences, a lot of studies, but with different results. So various studies show different outcomes. Some say LLMs do not plan with a more pessimistic ways, other with an optimistic review say that they can plan or they will plan. And different articles use different evaluation criteria with different benchmarks and metrics. But what we want to obtain from them, we want to assess their reasoning capabilities, we want to use them, evaluate them, integrate with symbolic tools or other things for our research. And in this paper, we seek to find some common ground among all these studies to build further research. So let's start with classical planning. We all know classical planning, and most of the papers use classical planning to evaluate LLMs. So given the initial state and goal of a problem, we want to study methods to obtain asynchronous actions, a plan to solve the problem in a deterministic setting with full observability with Boolean fluence. And large language models, or LLMs, are transform-based models trained on a large corpus of text. So for our literature selection, we selected studies published on conferences with peer review or journals or with substantial citations on archive with a major 20 or more citations. And our scope was to check what LLMs are applied to generate plans in the form of a policy or a heuristic in automated planning tasks. So we exclude, for instance, domain modeling and other categories like robotics, reasoning, or so on. And we selected more than 20 papers published in the last years on top conferences on deep learning, artificial intelligence, natural language processing, robotics, planning, and so on. Let's start talking about the transformer architecture. So, okay, this is a transformer architecture that can be divided into an encoder and a decoder. And very simply, we have some sentences in input, and we want to obtain some sentences in output. How? Well, inputs are going into the encoder will generate an embedded representation, and this will pass to the decoder. The decoder will generate the next word. This word is then appended to the start of the encoder, and this process is then repeated until we complete our sentences. We can also split the encoder and the decoder to obtain BERT and GPT. BERT is usually used for classification or regression tasks, such as heuristics, and we take again our sentences, we generate an embedding, and then we obtain a classification or regression. In GPT, instead, we use some inputs, we generate again the embedding, and we generate words iteratively, obtaining then our output sentence. And the main core block of all this process is the self-attention mechanism that let to pay attention to some parts of our sentence to insert this information into the embedding. So, what are our key points? Well, how LLM can be exploited, how are they evaluated, and what are their limitations. So, let's start talking about input and output. On my left, I have this figure that categorizes our papers based on the input and the output with natural language, PDDL, or hybrid, or value. So for input, we can have a problem, a domain inserted in natural language, exploiting what this model are trained for. So we have pre-trained models that are trained on large corpus of natural language, and also we can use some more formalism with PDDL or strips. And also we can have some kind of hybrid approaches where we integrate some PDDL formalism with some feedback in natural language. Also we can have some output, for instance, we want a plan in natural language, so to check and execute easily for human reading, or in a formal way to check from some validators in PDDL, or also we can obtain, for instance, using BERT, a heuristic value that can be then inserted into the search. So how LLM are used? Well, first, let me introduce prompting. So give an input sentence or more. We give this sentence to the LLM, and the LLM will produce some outputs. This is simply prompting. When we are talking about zero prompting, we are talking about a prompt with 0 examples of the task to solve, while with the few shot prompting, we are giving to the LLM also some examples of the solved task. And usually in this kind of categories, LLMs does not plan, and they have pretty much no capabilities of solving any plans, even simple ones. Then we can move to chain of thought prompting, where we want to obtain some reasoning step from the language models, also dilating with it using some form of external validators that can enhance our approaches. And finally, we can have fine-tuning. So given a pre-trained LLM, we then use some specific dataset to inject some knowledge or training from scratch. For instance, here we can evaluate ChatGPT and so on. Here we can have some approaches that will generate a Python policy given some Python interpreters or also val. And here we can have like Plasformer or PlanGPT that will try to solve some problems. So for our planner integration, we can evaluate LLMs as a standalone. So what is the knowledge inside these huge models? We can have a feedback with a validator, as I was telling before, with the chain of thought, or also with a more deeply integrated way and use validators inside the generation as masking tools and so on. Or we can integrate the LLM with a planner or a search. For instance, if we have a heuristics, we can compute a 3D best first search or a Monte Carlo tree search. And also there are some papers that tries to obtain a candidate plan from the LLM and then repair it with a planner, or also obtain some nodes that can be interesting from which we can start a search. As evaluations, we have different benchmarks that can be used. For instance, we have PlanBench, that is a natural language dataset with 3 domains, Blocksword, Logistic, and Mystery Blocksword. With over 600 instances, we have our international planning competition with a lot of domains, but with a few small number of problems, and also other benchmarks. And what papers are trying to evaluate? Well, first, all the papers evaluate valid plans generation, of course. Some of them also check if the plan is optimal or not. Other ones tries also randomization of object names, and this is very important in this field because for planning, usually the object names are quite changeable because they are only placeholder, but here they have meanings because we are working with a neural model that have meaning to our words. So changing them can affect their reasoning, and this is a very different thing than planners. Also, generalization to more complex problems is very important because we must test more and more complex problems in prompting or out of distribution samples in training and fine-tuning. So, can LLMs plan? Well, usually approaches that fail to plan are usually taken off the shelf through prompting strategies. Standalone LLMs will not plan, at least right now, with ChatGPT, Gemini, or so on, or even reasoning ones can solve block-solved with 5 blocks. And instead, approach that demonstrate some, at least, planning capability usually trains or fine-tunes LLMs. Also, approaches that combine LLMs with symbolic tools show the best results, as for instance in Silver with the generation of Python policy or the integration with some trained ones to obtain some sound generation and so on. However, in terms of generalization, to date, LLMs fail to solve complex planning problems. And usually also approaches that trying to train or fine-tune will not go very far away on the object scale. So, what are some challenges in measuring LLM's performance? Well, first, evaluating neural models requires many samples to ensure reliable performance estimates, and this is kind of a different thing compared to planners, because we don't have any formal properties, and so we need to compute many samples in the test, and this is a kind of thing that must be addressed right now. Also, since pre-trained LLMs acquire their knowledge through natural language, replacing meaningful text with gibberish can distort evaluation outcomes. For instance, if you think about a truck in logistics that can be driven in the city, the LLM know that that truck is something that can be driven on. But if we substitute the truck with some, for instance, chocolate cookies, the chocolate cookies will not be driven around the city for the language model. So we must perform some meaningful randomization to obtain the certain outcomes. Also, assessing complex planning tasks is essential because some papers try to assess that they can plan evaluating with 5 blocks on Bloxworth, and that's kind of a trivial problem. Also, some limitations. Training and evaluation of LLMs require huge computational resources with the servers, GPUs, and some of them are restricted under API. Some proprietary ones that are being used are more than ecosystem of LLM combined with others rather than only LLM, and this can distort evaluations. Also, usually we don't have all the properties of completeness, soundness, and domain independence. No LLM is complete. Some LLM can be sound with the integration of the validator, and usually prompting pre-trained domain in prompting, pre-trained LLM in prompting are domain independent, but usually they don't plan, while training or fine-tuning are domain dependent. And a very important question that for now no paper has asked is that LLMs mimic the plan to solve a problem, or is it the result of reasoning or copy and paste? This is a kind of interesting way. So, we investigated the role of LLMs in the generation of plans. We analyzed different papers showing some limitation and some evaluation. And out of our different approaches, the paper that showed the integration of LLM and symbolic tools can be an interesting direction for future works. Naturally, the landscape has evolved since the paper submission last year. Newer studies appeared through none represent a breakthrough, so if you have one, send it to me, please. And LLM continue to advance, but their true planning ability are still debated. Also, recent approaches like reinforcement learning aim to strengthen planning performance, but must still be evaluated. So I thank you, and I'm here for any questions.
Thank you very much. Are there any questions in the audience?
So one important assumption in planning is domain independence, because you essentially want to capture the strategic reasoning of the planner, so you don't want to get confused with the specificity of a certain domain. But if you're using LLMs, maybe you want to use the specific knowledge on the domain that comes from this sort of common knowledge the LLM has. So maybe when we look at planning with LLM, we should drop this point that is so foundational for planning.
Okay, usually the ones that works actually are domain-dependent ones. They are usually trying to obtain a Python policy or a heuristic for the specific domain, or are trained on that specific domain to obtain something more than the domain-independent heuristics. So right now, that's pretty much the landscape.
Any more questions? Okay, so now that you have read all of these papers,
Yeah.
I believe, you can be our oracle. Where will we be in like 2, 5, or 10 years with this?
I actually don't know. I think that there are some interesting directions, like assessing what are doing in terms of word modeling inside the LLM, or reinforcement learning to enhance capabilities, or neurosymbolic integration, like some symbolic tools with neural models in broad general category of LLMs and other learned system tools.
Questions?
So I would like to ask, you mentioned in one of the slides that if you combine LLMs with some symbolic reasoning, so it gives you better results. So I'm wondering, so do you assume that you have a symbolic model on of the environment for that, or do you use LLM to somehow obtain it and then do symbolic reasoning?
In the paper analyzing, in the disposition paper, we always have the symbolic environment. But for instance, there are papers in reinforcement learning, like Decision Transformer in 2020, that use a simulator with images as input, and then we don't have any formal model of the environment, and they train a GPT model to actually plan in Atari or in Mujoku.
Okay, thank you.
We have time for one more question.
I would like to know what's your idea about VLM. And I remember that Meta, they tried to train a VLM based on some kind of world model. And do you have any thoughts about that? Do you think that's also kind of planning?
Well, I think it is quite interesting working with the world models, because we can inject some knowledge about the domain inside the model that then we will use to plan. Also, VLM are quite useful because we don't always have our domain. We want to learn from traces, we want to learn from images, and I didn't read much VLMs on planning, but in other, like robotics or reinforcement learning, there are a lot of approaches that tries to use VLM to obtain a sequence of actions.
Okay, so let's thank the speaker once more.